Hi everyone, welcome back to JDCodebase. This is the day 39 of our LeetCode 75 study plan. If you are new here, every single day we pick one problem and we break it down simply, no fancy word, no confusion, just plain understanding. And today problem is the binary tree right side view, LeetCode number 199. It sounds like a big name, but the idea behind it is really simple. Once I show you the picture, you will get it immediately. So let's get into it. So the problem says, given a binary tree, imagine you are standing on the right side of it and looking at it. Return the value of the nodes you can see, order from the top to bottom, and that's it. So that is the whole problem. Let me make this super visual so it clicks right away. Imagine you are standing outside a building, looking at. Imagine you are like there are two buildings. One is left. This is the top. One is left. One is right. You are at the top of the building. You see yourself, means that is the first floor. Then you come at the second floor of this from one building. You see at this position, at this 2. The next the right side you see the 3 here, same as the 5. You again you down the floor, you see the 4. So this is our answer. So each floor is a level of the tree here, and each room is each floor is a node here, and we want to the rightmost node on every level. Means there might be other floors also, like 2, 3, 6, then 7. You do not have to consider that. You only have to care about this 3 and 4, because only you can see these floor directly from your eye, not the 6 or not the 7. So you have to find this way. And remember, the binary tree does not have this, just 1, 2, 3, 4, 5. So just go through the tree level by level. At each level, pick the last node. And to go level by level in a tree, we use something called the BFS, that is the breadth first search. BFS just mean visit the tree row by row and left to right. So to do BFS, we use a queue data structure in this. A queue is just an array where you add things to the back and take things from the front, like a linear at the top. And first person in first person out. This is the queue. Everyone knows the queue data structure. So our plan is the put the root node in the queue first. Then note how many nodes are in the queue. That is your current level size, and go through exactly that many nodes. The last one is your right side view, and save it. And while going through those nodes, add their children to the queue for the next level, and repeat until the queue is empty. Like I am at this position 1, then I just take this one in the queue, and in the result also I move towards down the tree. Then I get at the 2 and 3 here. We have to only take the last one element, that is the 3 here, and remove this 2 from the queue. And at the same time, we also have to push these value 5 and 4, and we have to take this 3 value in the resultant array. Same here, 5 and 4 come, remove this 5 and take this last one value in the queue, that is the 4 here. So we have to repeat until the queue is empty. So let me write the code here so you understand it. This is our main function, right side view, and it takes the root as the input. Root is just the top node of the tree, and if root is the empty, then return null here. Sorry, return the empty array, because we have to return the array for array format. And first, this is the safety check for any root. Means if the tree is empty, there is nothing to see. Oh, so we just return an empty array and stop here. Next is the make a resultant array, a empty array. This is our result array, and we will keep adding the rightmost node value here as we go up level by level. Next is the const qui is equal to root value. Means we create our qui, put the root node value in it, and complete node we have to push into this, and this is our starting point. Root is the first one in the line. Next we have to start a while loop, while qui dot length is greater than 0. Means we keep looping as long as there are nodes in the qui, and once the qui is empty we have visited everything and we stop. Now declare a value level size, and here level size is the qui dot length. So this level size is like before we start the processing the level, we take a snapshot how many nodes are in the qui right now. And this is very important here because as we process this level, we will be adding the next level nodes into the qui. If we do not save the number number now, so we will lose the track of where this level ends and the next one starts. Like I have this one, and I just push these 2 and 3 into the qui and remove this one from the qui. So here level is the 1, means qui dot length is 1, qui dot length is 2. Now this same processing is running. I just store the qui dot length into the level size as the 2, and at the same time I am pushing the value 5 and the 4 and removing this 2 and 3 value. So we have to always take out the row value, means row dot length, means qui dot length every time. Now start a for loop for let I equal to 0, I is smaller than level size and I plus plus every time in our for loop. We loop exactly level size time, and only the nodes that belong to this current level, nothing extra. So just take out the node is equal to qui dot shift, and shift here is the remove the first item from the array and gives it to us. So we are taking the next node out of the qui to look as it. And if I equal to level size minus 1, means we are at the last of this qui, then result dot push node dot value, means I goes from 0 all the way to level size minus 1. And so when I equal to level size minus 1, we are at the very last node of this level. So that last node is what you see from the right side, and we push it from value into our result. And if node dot left value is as, so we have to push qui dot push node dot left, and same apply here. If node dot right, then push qui dot push node dot right side, means we add the children of this node into the qui, and left child first, then the right child. We check if they exist before adding, and because not every node has the children, so these children will be processed in the next level. And in last we have to just return the result from this. And after this whole loop finish, every level has been processed, we return our result array, and which has all the right side value from the top to bottom. And what happened? I think spelling mistake. So let me run this this solution. Yes, it accepted. Let's try to submit this solution. And yes, it accepted. So this is our complete solution for this. First we check the base case. If the root is empty or null value, then we return the empty array, and we initialize a resultant array as the empty array, and also initialize the qui with the root value, and start a while loop. It runs until the qui dot length has some until the qui has some values, And first we store the level size, like at this position I have 1, then increase as we go down towards the downside of the tree. And every time we start a for loop, we check, we just remove the initial node from the queue, and if it is the last value in the queue, we push into the resultant array. And if node dot has some values, so we push into the queue also. And if node dot right has some value, we push into the queue also. But the loop runs on only till this level size, not the extra. And in the last of this entire tree traverse, we return the resultant array. And now let's talk about the time and space complexity for this. We visit every single node in the tree exactly one time. So if the tree has n node, we'll do n step here, and that is the big of n time complexity. We cannot do better than this because we have to check every node to find the rightmost one. And here space complexity also big of n, because we hold nodes as we go down, and the biggest level of the tree can have roughly half of all the nodes. So in the worst case, the queue hold n divided by 2, but that is still big of n. And that is the day 39. The whole trick of this problem was simple: go level by level. At each level, last node is what you see from the right side, and we use a queue to go level by level, and we use the level size to know exactly where each level start and end. So this pattern is called the BFS with the level size. Is one of the most useful pattern for the tree problems. Once you understand it, here you will see it again and again in the future problem also. If this click you for you today, that is a big win. Give yourself some credit also. If this video helped you, please hit the like button. It genuinely helps the channel grow. Subscribe to JDCodebase if you have not already. We are going through all the 75 problem one by one every single day, keeping it simple. And drop a comment below if you have any question. I read every single one. See you in the tomorrow on day 40. Keep going, keep growing.